In this session, we'll take up a problem on design of tension members. So we'll go for determining the design tensile strength of a tension member, and the problem what has been given is over here. So a single unequal angle ISA 100 by 75 by 6 is connected to a 10 thick gusset plate with 6 bolts of 16 diameter. You need to determine the design tensile strength if the longer leg is connected to the gusset plate and the pitch and edge distance are given as 40 the grade of steel is Fe410. So with that you need to find what is the design tensile strength. So for the tension member we have the design tensile strength given in terms of yielding, rupture and block shear. So we'll go for calculating what is the design tensile strength based on these three criteria. Later we'll decide the design tensile strength of the tension member. So we'll be referring to clause number 6.2, 6.3 and 6.4 of IS 800 2007. So the first criteria is the design strength due to yielding of gross cross section, that is 6.2 in page 32. So it is given by TDG, which is equal to AG into Fi divided by gamma m naught. AG is the gross area of the section over here, and this gross area we can find it in steel tables. So if you refer to the steel table and look for this unequal angle section ISA 100 by 75 by 6, you'll find that the gross area is 10.14 centimeter square, or it is 1014 square. So that will be the gross area, and yield stress in this case, grade of steel is Fe410. So yield stress will be 250 Newton per square, Fi, and the factor of safety governed by yielding, that is the resistance governed by yielding, is given in this table phi of IS 800. So if you refer to this resistance governed by yielding, it gives you gamma m naught, which is 1.1 factor of safety based on yielding. So that has been taken over here, 1.1, and this gives us the design strength due to yielding as 230.45 into 10 raised to 3 newtons, that is nothing but 230.45 kilonewtons. This is one of the strength what we have. Now the second is due to rupture at the critical section. So this is in the clause 6.3 of page 32 and 33. You'll find this clause given over there in IS 800. So since it is an angle section and only one leg of the angle section has been connected, as it is shown in this figure over here, the longer leg has been connected to the gusset plate. It was given in our question also, the longer leg is connected to the gusset plate. So this is the longer leg, 100 and it is connected with the help of 16 diameter bolt, 6 number of 16 diameter bolt. In this row there are 6 number of bolts over here. So this, in this case, the rupture strength TDN is expressed with this equation, 0.9 ANC Fu upon gamma m1 plus beta into Ag naught into Fi upon gamma m naught. So ANC is the net area of the connected leg, Ag naught is the gross area of the outstanding leg. So what is ANC? The net area of connected leg will be 100 total width of the leg minus the bolt hole diameter 18 minus half the thickness. We'll be taking half the thickness in this longer leg and half the thickness in the shorter leg while calculating the areas. So minus half the thickness of the angle into the thickness of the angle. This comes out as 474 square. So this leg net area, the net area of the connected leg is 474 square. Similarly, if I calculate the gross area of the outstanding leg, so there will not be any deduction made for bolt holes in this case. It is a gross area. So width of the outstanding leg is 75 and so that is 75 minus half the thickness. So 75 will be this full width. In that, half the thickness has been deducted over here. So that sum 75 minus 6 by 2 into the thickness of the angle. That will be the area of this outstanding leg, with the gross area of the outstanding leg over here. So that comes out to be 432 mm square. So ANC and AG naught, we got them. Now beta, what is the value of beta? So the beta is given by this equation, 1.4 minus 0.076 into WIT into Fi by Fu into Bs upon LC. So W is the width of this outstanding leg, 75 mm, T the thickness of the angle, 6 mm, Fi yield stress 250, Fu ultimate stress 410, Bs, this is given by this equation, W plus WL minus T. So W width of outstanding leg plus WL will be this distance from the center of the bolt hole up to the end of this angle section at this point, up to this point, from the center of bolt hole up to this root of this angle section. So what we have is the edge distance is given to us as 40 mm. So in this connected leg, which is of 100 mm width, 100 minus 40 will give us what will be our WL. So that will be 100 minus 40, which is 60 mm over here. And BS comes out to be 75 plus this WL, that is 60, minus T. So it comes out as 129 mm. So BS is 129 mm. LC depends on the number of bolts that have been provided in the connection. So LC is the length of the connection, that is the connection from the first bolt up to the last bolt in the connection, distance from the first bolt up to the last bolt over there. So in this we have 6 bolts provided in the connection. So from that 6 bolt, what we have is we come across 5 pitch distances. So LC will be 5 into 40 mm. Okay, so that will be 200 mm over here. So that will be the value of LC. If you substitute for these W, T, Fi, Fu, Bs and LC, beta will come out to be 1.02. Now beta is having a upper limit and lower limit. The upper limit is Fu into gamma m naught divided by Fi into gamma ml. So Fu 410 into gamma m naught 1.1 divided by Fi 250 into gamma ml, which is 1.25. So this will be 1.44. This is the upper limit. The value of beta should not be more than this. And at the same time, the lower limit is 0.7. Value of beta cannot go below this. If at all the beta is exceeding these values, if it is going above 1.44, take it to be 1.44. If it is coming below 0.7, take that to be 0.7. So in this case, it is between 1.44 and 0.7. So I'll be taking the beta value what has been obtained over here, 1.02. So with that, the rupture strength, when you substitute for all these values, ANC, AG naught, beta, Fi, Fu, and the factor of safety is, you'll find that the rupture strength due to in this tension member is 240.07 kilonewtons. So that is the second criteria, or second rupture strength of the tension member due to rupture. And one more what we have is the strength due to block shear, TDB, which is given by these two equations over here. So in case the yielding is along the shearing plane, along this plane, so it will be this equation which will be giving us the strength under block shear. So what we need to find is what is the net and gross area along the shearing plane and what is the net and gross area along this tension plane, and substitute them in this particular equation. So Fi, Fu, they are the stresses what we have, the yield stress and ultimate stress, and we have also seen what is gamma m naught and gamma ml. Okay, so gamma m naught, factor of safety for yielding 1.1, gamma ml factor of safety for ultimate stress, it is 1.25. Now coming to AVG. AVG is the gross area along the shearing plane. So it will be the length of this line from the center of this bolt up to the end of the angle multiplied by the thickness of this angle. So this comes out to be 40 into 6 to 40 into 6. So there are 5 pitch distance and 40 mm end distance over here. So for this will totally come out to 240 mm. That multiplied by the thickness of angle will give us the area along this shearing plane. This is the gross area. We have not made any deduction for the bolt holes. So that will be the gross area, AVG. Now AVN, what we have is, here we need to make the deduction for bolt holes. What we come across is 1, 2, 3, 4, 5 and half bolt hole over here. We come across 5 and a half bolt hole. So 240, the same length of the line along the shearing plane, 240 minus 5.5 bolt holes. Bolt hole are of 18 mm diameter, so minus 5.5 into 18 multiplied by the thickness of the angle. So that comes out to be 846 mm square. This is the net area along shearing plane. Similarly, the gross area along tension plane will be this distance multiplied by the thickness of the angle. So this is the edge distance what we have here. So 40 into 6, it will be 240 mm square. The net area along the tension plane, 40 minus half the bolt hole diameter, will come across half the bolt hole diameter along this tension plane. So 40 minus 0.5 into 18 into 6, that will be 186 mm square. So I have these four areas, the gross area and the net area along shearing plane, the gross area and the net area along the tension plane. So what I'll be doing is I'll be using them in these two equations. So in case of first condition, that is shearing, yielding is taking place along the shearing plane and rupture is taking place along the tension plane, the strength comes out to be 243.85 kilonewtons. And in the second case, so wherein the rupture is taking place along the shearing plane and yielding is taking place along the tension plane, if you substitute for AVN, ATG and the stresses over here, you'll find that the strength due to block shear is 198.73 kilonewton. So out of these two, whichever is least, that will be considered as the strength under block shear. So in this case, what I have is 198.73 as my block shear strength. So TDB will be 198.73. Now coming to the strength of the tension member, it will be least of the three values what we have calculated, that is TDG, TDN and TDB. So out of these three, if you compare them, TDG is 230.45 kilonewton, TDN, that is due to rupture, it is 240.07 kilonewton, and under block shear it is 198.73 kilonewton. So this is the least one. So I'll be taking the design strength of tension member as 198.73 kilonewtons. So this is how we go for calculating the design strength in case of tension member and mainly in case of angles what we had seen in this problem.